Picture this. You're in the right seat of a Boeing 737-200. You are accelerating down the runway at Cape Town International Airport.
Okay, heavy and fast.
Yeah, exactly. It's November 2007, and this is Nationwide Airlines Flight 732. You hit V1, your decision speed. You hit VR to rotate.
Right, the critical moment.
You pull back on the yoke, the nose lifts,
Yeah.
the main gear leaves the tarmac, and at that exact, critical millisecond of flight, there's a massive, violent shudder. The aircraft yaws incredibly hard to the right.
Oh, wow.
And out the window, you see something that just completely defies logic. The entire right engine has physically separated from the wing and fallen right onto the runway.
I mean, that's the absolute worst case scenario, right?
Unbelievably.
Because you are heavy, you're slow, you're fighting this massive asymmetric thrust, and you are just hundreds of feet in the air with half your power completely gone.
It's terrifying. But welcome to the deep dive, everyone. Today, we are custom tailoring this entire conversation directly for you, the aviation student.
Because you're the one preparing to sit in that pilot's seat.
Exactly. You are the one who will bear the ultimate legal and moral responsibility for the aircraft, your crew, and the passengers. And we have a massive stack of ground school flight planning sources in front of us today.
Yeah, we've got slide decks, dense performance manuals, specific tables from Shike 697.
Which is essentially your flight planning Bible, let's be honest.
Pretty much, yeah. And we have the PartSat regulations that govern all of commercial air transport.
It's the kind of highly technical, heavily regulatory web that usually makes student pilots go completely cross-eyed when they're prepping for their ATPL exams.
Right, but we have to remember it's also the mathematical architecture of survival.
Okay, let's unpack this. Our mission for today's deep dive is to zero in on two of the most critical, life-saving concepts in all of flight planning. The point of equal time, which we call the PT, and the point of safe return, the PSR.
Two absolute pillars of flight planning.
Right, so we're going to extract the vital nuggets from all this dense material. We're going to translate the heavy abstract math into intuitive logic and explore why these coordinates actually matter.
So you never forget them in a high-pressure exam, right?
Exactly. And more importantly, so you can execute them flawlessly in a dark cockpit over the ocean.
And that context is key because, in the cockpit, you don't have the luxury of time to flip through a textbook. You can't just try to remember some formula you learned a year ago.
Yo, absolutely not.
These concepts need to be second nature. They have to make intrinsic, logical sense to you.
So let's start with what this all means for standard flight planning. Because before we get into the heavy contingency math of PC and PSR, we really have to establish why these concepts even exist within the standard fuel planning framework.
Right. Why do the regulators even require them in the first place?
Exactly. To understand the exception, we have to understand the rule. So what's the baseline here?
Well, if we connect this to the bigger picture, standard fuel planning, like the standard fuel scheme outlined in your EASA and FAA sources, it's fundamentally built on optimism.
Optimism, really?
Yeah, it really is. It is designed for a normal flight experiencing, normal everyday aviation friction.
Okay, so by friction, you mean a slightly stronger headwind than the forecast predicted?
Yeah.
Or maybe getting vectored around a pop-up thunderstorm?
Exactly that. Or being put into a holding pattern because someone blew a tire on the runway at Heathrow and everything is backed up.
Right, the daily grind stuff.
Yes. And if you look at the basic fuel ladder for performance class A, B, and C aircraft, it actually perfectly accounts for those daily inconveniences.
Let's walk down that ladder. You start with your taxi fuel, right?
Right. And a lot of students think taxi fuel is just the fuel to roll from the gate to the runway, but it's not.
It's more than that.
Much more. It includes the fuel your APU, your auxiliary power unit, burns while you are sitting at the gate providing air conditioning and electrical power before the main engines even start. And
the sources note a really interesting detail here about weight. So Jet A1 fuel has a specific gravity of around 0.8, meaning 100 liters weighs about 80 kilograms.
Right, it's heavy stuff.
So you aren't just burning fuel during taxi, you are actively shedding significant weight just getting to the holding point.
Which is a huge factor for your takeoff calculations, But once you're lined up on the runway, you move into the trip fuel.
That's the meat and potatoes of the flight plan, right?
Exactly. It covers the takeoff roll, the climb to your initial cruising level, the cruise itself, and that includes any planned step climbs as the aircraft gets lighter and can reach higher, more efficient altitudes.
Right, because you burn off that heavy fuel
Yeah.
so you can climb higher.
Yep. And then it covers the descent to the start of the approach procedure and finally the approach and landing at the destination aerodrome.
Okay, so that's the optimistic plan. But here is where the buffers start to kick in. After trip fuel, the next one up is contingency fuel.
The buffer for the unknowns.
Right. And the sources state this is generally the greater of 5% of your planned trip fuel or 5 minutes of holding fuel at 1,500 feet above the destination aerodrome in standard conditions.
Which naturally raises an important question for students, right? Why 5%? Like, where does that specific number come from?
I always wondered if it was just an arbitrary guess by some regulator in the 60s.
Well, historically, weather forecasting and wind modeling were just much, much less precise than they are today. That 5% buffer was instituted to cover the unpredictable nature of the atmosphere.
Unforecasted headwinds, things like that.
Exactly. Or slight deviations in routing by ATC. There are modern variations now, like, reducing it to 3% if you nominate an en route alternate, or using a decision point procedure.
But broadly speaking, it's a relatively small buffer meant for minor deviations.
Exactly. It's not meant to save your life in a catastrophe.
Okay, so after contingency, you have alternate fuel. So if you get to your destination and, let's say, the fog has rolled in and visibility drops below your legal minimums, this fuel covers a complete missed approach.
A climb back up to a cruising altitude.
Right. The transit to your nominated alternate airport, and the descent and landing there.
And then finally, sitting at the absolute bottom of your tanks is the final reserve fuel. This is the sacred, untouchable fuel under normal circumstances.
You don't mess with the final reserve.
Never. For piston engines, regulations dictate 45 minutes of flying time. But for turbine engines, jets, and turboprops, it's 30 minutes of flying at holding speed at 1,500 feet above the alternate, or above the destination if no alternate is required.
Wait, why the difference there? Why do piston aircrafts get 45 minutes, but turbines only get 30?
It really comes down to how different engine types process air and burn fuel. Turbine engines are incredibly efficient at high altitudes where the air is thin and extremely cold.
Right, they love the flight levels.
They absolutely do. But when they are forced down to 1,500 feet into thick, dense, warm air, they gulp fuel at an astonishing rate.
Ah, okay.
So if a heavy jet is holding at 1,500 feet, 30 minutes of fuel is a massive physical volume and weight to carry around for the whole flight.
It penalizes the payload.
Heavily. Piston engines, on the other hand, are much more consistent in their fuel burn across altitudes, so providing a 45-minute buffer doesn't penalize the aircraft's payload capacity anywhere near as drastically.
That makes a lot of sense. And the sources are completely unequivocal about this final reserve. You should not normally land with less than this amount of fuel on board. It is the absolute regulatory red line.
Exactly. And beyond that, you might carry extra fuel for anticipated delays or discretionary fuel, which is, purely at the commander's discretion.
The captain's extra peace of mind.
Precisely. So that is the ladder. Taxi, trip, contingency, alternate, final reserve.
Okay, so here is where we transition from standard planning into the high-stakes game of what if. As an aviation student, you know that standard 5% contingency fuel is great if ATC gives you a vector that adds 20 miles to your route.
Sure, it handles that perfectly.
But my question for you is this. Is that 5% enough to save you if you suffer a massive systemic failure halfway across the Atlantic Ocean?
It is wholly, completely inadequate, and that is the crux of the issue. That's the entire reason these sources and formulas exist. The standard fuel scheme just completely breaks down when confronted with a catastrophic emergency.
So let's explore the physics of that breakdown. Let's say you're flying a twin-engine jet over a sprawling desert or a massive mountain range, and you suffer an engine failure or maybe a sudden explosive loss of cabin pressurization.
Either one is a nightmare.
What actually happens to the aircraft's performance in those moments?
In either of those scenarios, your highly optimized flight profile is just instantly destroyed. Let's take the depressurization scenario first because it's so extreme.
Okay, run us through it.
If your cabin loses pressure at 35,000 feet, the time of useful consciousness for the crew and passengers is measured in seconds. You must initiate an immediate, incredibly aggressive descent to an altitude where humans can breathe without supplemental oxygen.
Which is universally accepted as 10,000 feet, right?
Yes, 10,000 feet.
We touched on this earlier with the reserves, but as an aviation student, you know the aerodynamics here. Down at 10,000 feet, The air is exponentially thicker than at 35,000 feet.
It's like flying through soup compared to the upper atmosphere.
Right. Thicker air means massive parasite drag.
And to push the airframe through that thick, drag-heavy air at a speed that actually keeps you flying, your engines have to work much, much harder. So your true airspeed plummets, and your fuel consumption per mile just skyrockets.
And the same basic logic applies to an engine failure, doesn't it?
Absolutely. If you lose an engine on a twin jet, you instantly lose 50% of your thrust. You physically cannot maintain 35,000 feet on one engine.
You literally don't have the power to stay up there.
No, you have to execute a drift down procedure to your single engine service ceiling, which, depending on your weight, might be somewhere around 20,000 feet.
So again, lower altitude, thicker air, more drag.
Exactly. And now you are asking one single engine to do the work of two.
So in both of these emergencies, your beautifully planned trip fuel burn goes right out the window. Suddenly, you are burning fuel at a rate that is going to vaporize your little 5% contingency in a matter of minutes.
It becomes mathematically impossible to complete your route as planned. You cannot make it to the destination.
So you have to divert.
You must divert. But here's the catch of diversion isn't just pointing the nose toward the nearest dot on the GPS screen. You have to ensure you actually have the fuel to reach that dot.
And this is where the concept of additional fuel enters the AC regulatory framework, right?
Yes. The sources mandate that if your standard fuel isn't enough to cover a critical failure at the absolute most critical point along your route, you have to load additional fuel before you even take off.
The regulation actually states you need enough fuel to suffer the failure, drift down to the lower altitude, fly to an en route alternate airport, hold for 15 minutes at 1,500 feet, make an approach, and land.
But here is the massive architectural challenge for the pilot. To know how much fuel it takes to survive a failure at the most critical point, you first have to figure out exactly where that critical point is geographically located in the sky.
You have to find the dot. And as a reminder to the listener, as the pilot in command, the legal responsibility for ensuring there is sufficient fuel to cover these unplanned diversions falls entirely on you.
No pressure, right.
Right. When you sign that load sheet and flight plan, you are taking legal ownership of that math.
Which brings us perfectly to the first of our two critical calculations, the point of equal time, or PEAT. It is also sometimes referred to in older texts and in some airline operations manuals as the critical point, or CP.
Okay, let's unpack the point of equal time. The definition provided in the ground school sources is wonderfully concise. It is the point on your route where it takes the exact same amount of time to continue forward to your next suitable aerodrome as it does to turn around and return to your previous suitable aerodrome.
Right, and time is the operative word there, not distance. We are calculating equal time.
And that makes perfect sense if you think about it, because fuel burns by the hour, not by the mile.
Exactly. Your engine doesn't know how much ground you've covered. It only knows how many minutes it's been running.
So in a perfect vacuum, or let's say in perfectly still air with zero wind, calculating the key ET is incredibly simple. It's exactly halfway between the two airports.
Simple geometry. If Airport A and Airport B are 1,000 nautical miles apart in zero wind, your PT is at exactly 500 miles. Assuming your true airspeed is a constant 500 knots, it takes you exactly 1 hour to go back and 1 hour to go forward.
But the reality of aviation is that we never, ever fly in perfectly still air. The atmosphere is a chaotic, constantly moving ocean of air masses.
Which is why this next concept is so important.
Yeah, this is the most vital conceptual leap you must make as an aviation student regarding PE. The sources state this as a golden rule, and it is heavily bolded in the slide decks. The PEAT moves into the headwind.
And it is entirely counterintuitive for a lot of students at first glance. They always ask, why does the point of equal time shift? Why doesn't it just stay in the middle?
I know I struggled with that at first. I think the best way to visualize this isn't in the air, but on the ground. Think of one of those flat, moving walkways you find in massive airport terminals.
Oh, that's a great analogy.
Right. Let's say you are standing on a moving walkway that is 100 meters long, and it's moving forward at a pretty brisk pace. If you start walking forward in the same direction the belt is moving, your walking speed is combined with the belt speed. You are absolutely flying toward the end of the walkway.
You basically have a massive tailwind.
Exactly. But what happens if you realize you drop your passport halfway down the walkway and you have to turn around?
Well, now you are walking against the belt. You are fighting the machinery.
Every step you take forward is partially canceled out by the belt pulling you backward. You are crawling relative to the ground. You have a massive headwind.
So if we translate that to finding a point of equal time, a point where it takes you the exact same amount of time to reach either end of the walkway, that point physically cannot be in the middle.
Right, because if you are in the middle, turning back against the belt will take much longer than letting the belt carry you forward.
Exactly. To equalize the time, your critical point has to shift much closer to the start of the walkway.
That way, you only have to fight the belt for a short distance to get back, while you have a long distance to travel forward, but you'll cover that long distance quickly because the belt is helping you.
The point of equal time shifts into the headwind.
What's fascinating here is how the mathematical formula perfectly and elegantly captures this physical reality.
Yeah.
You don't have to guess where that point is. You can calculate it down to the decimal. We are trying to find the distance to the PTT.
And the formula for that is beautiful in its simplicity once you get it.
The sources provide the classic PET formula. It's basically a proportional ratio. Distance to the PET, which we will call P, equals the total distance between the two suitable airports, which we'll call D.
Okay, D for distance.
Right. You multiply that total distance by your ground speed home, meaning the ground speed you would have if you turned around and went back. Let's call that H.
Got it. H for home.
So the top of our fraction is total distance times ground speed home, D times H. Then you take that number and divide it by the sum of your speeds, ground speed onwards, which is O plus ground speed home, H.
So the formula is P equals D times H divided by O plus H.
It looks like alphabet soup when you write it on the whiteboard, but let's apply the logic to a practical example from the slide deck. Let's say an aircraft is tracking from point A to point B. The total distance D is 1,200 nautical miles.
Okay, 1,200 miles.
The flight computer calculates your ground speed outbound, O, is 220 knots. But if you were to turn around, your ground speed homewards, H, would be 240 knots.
Okay, let's pause and analyze those inputs for a second. If your speed homewards, 240, is faster than your speed outwards, 220, that means the wind is pushing you when you go home.
Which means right now, flying outward, you are fighting a headwind.
Exactly. And if we apply our golden rule, the PE moves into the headwind, we should expect our calculation to push the PET further down the route, past the halfway mark, closer to the destination where the wind is coming from.
Let's see if the logic actually holds up to the math. Total distance D is 1,200. We multiply that by ground speed home, H, which is 240.
So 1,200 multiplied by 240.
That gives us 288,000. That's the top half of our ratio. Now for the bottom half, we add the two ground speeds together. Ground speed out, 220, plus ground speed home, 240 equals 460.
So we just divide 288,000 by 460.
Which gives us a distance to the PET of precisely 626 nautical miles from departure.
And since half of our 1,200-mile route is 600 miles, the PET has indeed moved past the midpoint.
It's at 626 miles. It has moved 26 miles into the headwind.
The math mathematically forces the coordinate to shift exactly as the physical analogy suggested it would.
It's so satisfying when the numbers back up the theory like that.
It really is, and that underlying logic is crucial because the math in the real world gets far more complicated than just simple A to B distances.
Let's take this out of the realm of abstract variables and put it into a high-pressure, real-world scenario. The sources provide a brilliant case study on threat and air management, or TEM, regarding a one-engine inoperative scenario.
Ah, yes, the OEI scenario. As an aviation student, you will absolutely see scenarios like this on your exams, and more importantly, they're going to throw this at you in the simulator.
It's a classic trap designed to see if you actually understand the physics of flight, or if you're just blindly punching numbers into a calculator.
Let's set the scene. You are the captain of a small twin-engine turboprop flying a commercial route from Aalborg up in northern Denmark to Manchester in the UK.
Okay, over the water.
Right. Your route takes you directly over the North Sea. It's a 300 nautical mile crossing. There are suitable airfields near your route on the Danish coast behind you at Esbjerg, and on the UK coast ahead of you at Newcastle.
But this 300-mile stretch of cold, unforgiving, stormy ocean is your critical sector. You need to know your PT.
Exactly. So here is the performance data you are given for the flight. Your normal, healthy, two-engine cruise is at flight level 200. That's 20,000 feet. Up there, your true airspeed is a steady 240 knots.
Nice and fast.
However, if one of those turboprop engines fails, you lack the thrust to maintain 20,000 feet. You are forced to perform a drift down to your single-engine cruise altitude, which the performance manual states is flight level 120 or 12,000 feet.
And at that lower altitude, struggling on one engine through thicker air, your true airspeed drops significantly to 180 knots.
So we have a change in altitude and a change in airspeed, but here is the most critical variable. The atmosphere is completely different at those two altitudes.
The wind aloft is not uniform.
Not at all. Your weather briefing shows that at your normal two-engine altitude of FL 200, the wind is blowing from 230 degrees at a brisk 60 knots.
Okay, 230 at 60.
But down at your emergency one-engine altitude of FL 120, the wind is blowing from 210 degrees at a gentler 40 knots.
So here's where we get to the absolute core of the threat and error management trap. You sit down with your flight computer in the dispatch room to calculate the PET distance for an engine failure. Which set of data do you use?
This is where so many people get caught.
Do you use your current normal two-engine data, or do you use the hypothetical emergency one-engine data?
The instinct for many students is to think, well, I am planning for the flight. I am actually flying right now. I should use the winds and speeds for the altitude I will be at before the emergency happens.
And if you follow that instinct, you calculate a coordinate that could literally leave you ditching in the freezing North Sea.
Because the point of equal time is exclusively about surviving the aftermath of the failure. It is a calculation of the time it takes to fly to safety after the engine has already quit.
After you have drifted down.
Right. And while you are actively flying on one engine, therefore, you must use the emergency performance data, the single engine airspeed and the lower altitude wind, to calculate the geographic location of the PET.
Okay, let's unpack the emergency math. Our one-engine true airspeed is 180 knots. We apply the wind at the single-engine altitude, the wind from 210 degrees at 40 knots.
We'll skip the complex trigonometry of the whiz-wheel flight computer for now, but the sources give us the resulting ground speeds.
Right. Fighting the wind on one engine, our ground speed outbound, O, is 140 knots. But if we turn around, the wind helps us, and our ground speed homeward, H, on one engine is 220 knots.
So we plug those emergency speeds into our proportional formula. Distance P equals the total distance, which is 300 miles multiplied by ground speed home, 220 knots.
300 times 220, that's 66,000.
We divide that by the sum of our ground speeds. Outbound 140 plus home 220, which is 360.
So 66,000 divided by 360 gives us a distance of the PET of 183 nautical miles.
So 183 miles from the Danish coast, if you lose an engine, it will take you the exact same amount of time to limp forward to the UK as it will to limp back to Denmark.
But the sources have a follow-up question here that springs a second trap on the student.
Oh yeah, they love this one.
Now that we know where the PET is, that's 183 miles away, how long does it take to reach that PE from the moment you take off?
And this is where you have to mentally shift phases of flight.
It's brilliant, really.
It is. To calculate the location of the emergency PET, we used emergency single-engine speeds. But to calculate the time it takes to reach that point from departure, you have to recognize the reality of the flight. You haven't had the emergency yet.
Right. You're flying out to that 183-mile mark with two perfectly healthy engines, sitting comfortably at your normal cruising altitude of 20,000 feet, experiencing the high-altitude winds.
Exactly. So to find the time to the PET, we take the distance we just calculated, 183 nautical miles, and divide it by our normal two-engine ground speed outbound.
Using the normal true airspeed of 240 knots and the high-altitude wind of 230 at 60 knots, the sources calculate that normal ground speed outbound is 181 knots.
So 183 miles divided by 181 knots equals 1 hour and 1 minute.
That is a phenomenal illustration of why aviation demands critical thinking. If you use the wrong speeds for the wrong phase of the calculation, your contingency plan is built on absolute fiction. You have to understand the timeline of the emergency.
And this TEM application goes far beyond just wind and distance. The sources explicitly highlight the dangers of terrain clearance during the drift-down phase.
Oh, this part is genuinely terrifying if you get it wrong.
There's a vivid, highly detailed graphic in the presentation showing an aircraft losing an engine and beginning its drift-down trajectory over a jagged mountain range.
Let's visualize this. Think about flying over the Alps or the Rockies. The graphic shows a twin-engine aircraft cruising at 19,000 feet. An engine fails. The performance manual dictates that given their current heavy weight, their single-engine cruise ceiling, the absolute highest they can stay in the air on one engine is 11,000 feet.
But the topographical chart shows that the jagged peaks directly below them have a minimum sector altitude, an MSA, of 13,000 feet.
Which means if they stay on their current forward route, their damaged aircraft will physically sink into the granite. They cannot maintain an altitude that clears the terrain ahead of them.
It's a fatal scenario. In this mountainous situation, calculating the PT isn't just about figuring out which airport is faster to reach, it's about calculating your escape hatch.
Right, you're literally finding the point where you can turn and run.
It's finding the critical point where if you lose an engine, you still have the altitude and distance required to turn around, reverse course, and fly out of the mountainous area before your drift-down trajectory intersects the peaks.
The math becomes a three-dimensional survival coordinate. You are ensuring your descent profile keeps you above the rocks. That is why PT isn't just a box you tick on a flight plan. It is a vital spatial awareness tool.
But as vital as it is, the point of equal time is fundamentally built on a premise of choice. It assumes you are choosing between two viable options. Do I go to airport A or do I go to airport B?
Right, you have a left or right option.
But what if the geography is so hostile or so staggeringly remote that airport B is your only option?
And that transition takes us out of the realm of mechanical emergencies and into the realm of pure geographical isolation. We move from the point of equal time to the point of safe return, the PSR.
Which is also known in some regulatory texts and operational manuals as the point of no return, or PNR. And while the math shares some DNA with the PET, it is a very, very different psychological and operational beast.
Let's lock down the definition based on the sources. The point of safe return is the furthest geographic point along your route where an aircraft still has enough fuel to turn around, fly all the way back to the departure aerodrome, and land with its required final reserve fuel intact.
To put it bluntly, once you fly past that specific coordinate, returning is no longer a mathematical possibility. The laws of physics and fuel consumption dictate that you are entirely committed to moving forward.
To understand why this concept is so intensely critical, the sources highlight the reality of isolated aerodromes.
Yeah.
They feature a photograph of Yushu Batang Airport in China.
If you haven't seen this place, it is incredible. It sits on the Tibetan Plateau at a staggering elevation of 12,812 feet above sea level.
Over 12,000 feet.
Yes, and it is surrounded by absolutely nothing but high-altitude wilderness, towering peaks, and thin, unpredictable air.
Or consider another example from the text, St. Helena. It's a tiny speck of volcanic rock sitting in the middle of the immense South Atlantic Ocean, literally thousands of miles from the nearest continental landmass.
If we connect these locations to the broader picture of standard fuel planning we discussed earlier, these airports completely break the system. Usually when you fly a commercial route, you carry alternate fuel. If the weather at your destination is bad, you execute a missed approach and fly to the next city. But for St. Helena, there is no next city.
It's just ocean.
Just ocean. There are no en route alternates you can divert to Midway, and there are absolutely no destination alternates.
You cannot physically load enough fuel onto the aircraft to fly from Africa to St. Helena, shoot an approach, realize you can't land because of fog, and then fly all the way back to Africa.
The fuel required for that return trip would be so incredibly heavy that the airplane would be over its maximum takeoff weight. It physically couldn't get off the runway. So you have a destination where once you arrive in its airspace, you are mathematically forced to land regardless of the weather conditions.
So as a pilot, what do? You can't just launch over the ocean, cross your fingers for 6 hours, and hope the weather is clear when you arrive. Aviation doesn't run on hope.
No, definitely not. And this is where the regulators mandate the predetermined point, or PDP procedure, which is intrinsically linked to the calculation of the PSR. Because you cannot carry fuel to an alternate after you arrive, you must establish a rigid point in the sky before you arrive where you make a final, binding decision.
The predetermined point.
Yes. When a dispatcher builds a flight plan to an isolated aerodrome, they will explicitly nominate this point based on the aircraft's fuel burn and the forecast winds.
So it's baked into the plan.
Exactly. And when the flight crew reaches this exact coordinate in the sky, they must make a binary, irreversible decision. They pull down the latest satellite weather data for the isolated island via ACARS or data link.
And they ask themselves, is the weather good? Is it above our legal landing minimums? Yes. We continue.
Right. Or, no, the weather is deteriorating, a storm is moving in, we turn back right now. Because if they fly even 5 or 10 minutes past that point of safe return, they will have burned the fuel required to make it back to the mainland.
It's the ultimate point of commitment. So how do we calculate exactly where that invisible line in the sky actually is? Let's get into the math.
The formula for calculating the time to the PSR is structurally very similar to the PET formula, but instead of focusing on the total distance between two airports, it focuses entirely on your fuel tanks. specifically how much time that fuel buys you in the air.
Okay, so what's the equation?
The formula is time to PSR, which we'll call T, equals your safe endurance, E, multiplied by your ground speed home, H. Then you divide that by the sum of your ground speed out, O, plus your ground speed home, H.
So T equals E times H divided by O plus H.
Exactly.
Okay, let's unpack the most important variable there, safe endurance. The sources define total endurance as the absolute maximum time an aircraft can remain airborne until the engines sputter and the fuel tanks are literally bone dry.
And we obviously do not use that for planning.
No, never. Safe endurance is the time an aircraft can remain airborne and burn all of its available fuel except the legally required reserves. You take your total usable fuel, subtract your final reserve fuel, subtract any mandatory holding fuel, and whatever time is left over, that is your safe endurance, represented by E.
Right. It's the fuel you are legally allowed to burn while still guaranteeing a safe landing. Let's run a straightforward example from the sources to see the PSR formula in action.
Let's do it.
Your total distance to the isolated destination is 1,200 nautical miles. After subtracting your reserves, your safe endurance, E, is exactly 5 hours. Your ground speed outbound is 540 knots, and your ground speed homeward is 460 knots.
Okay, wait, I have to push back here for a second and look at those speeds.
Go ahead.
If my ground speed out is 540 knots and my ground speed home is 460 knots, that means I have an 80-knot wind factor. I am flying much faster on the way out, which means I have a massive tailwind pushing me toward the destination.
You do.
Logically, if I have a massive tailwind on my way out to the island, I'm covering ground incredibly fast. I'm gobbling up the miles. So shouldn't my point of safe return be pushed really, really far away? I mean, I'm screaming toward the destination, so I should be able to fly much further before I have to turn around, right?
That is the single most common intuitive trap in PSR calculations, and it catches students all the time. You are absolutely right that you are covering ground very fast on the way out. But you have to remember the definition of the PSR. It is about the fuel required to get home.
Oh, wait.
A tailwind on the outbound leg means you are facing a headwind on the return leg.
Oh, of course. You turn around and hit a wall of air.
Exactly. And because you are fighting that 80-knot headwind to get home, your safe endurance, those 5 hours of usable fuel, gets eaten up much faster over a much shorter distance. The headwind aggressively punishes you on the return leg because fuel is time and fighting the wind costs time.
That makes total sense when you frame it like that.
Let's let the math prove it. Time to PSR equals 5 hours of safe endurance multiplied by 460 knots ground speed home. That gives us 2,300. We divide that by the sum of the ground speeds. 540 plus 460 is 1,000.
So 2,300 divided by 1,000 gives us a time to PSR of 2.3 hours or 2 hours and 18 minutes.
Yep.
Okay, so at 2 hours and 18 minutes into the flight, we hit the point of no return. And to find the geographic distance of that point, we just multiply that time, 2.3 hours, by our outbound speed of 540 knots. 2.3 times 540 gives us 242 nautical miles.
Correct.
Wait a minute. Look at the original variables. The total distance to the destination is 1,200 miles, but our PSR calculation says we can go out to 1,242 miles. Our point of no return is past the destination.
Which perfectly illustrates the math. Because you have such a massive tailwind on the way out pushing you along, you actually have enough fuel to fly completely past your destination, turn around, fight the headwind, and fly all the way back to your departure airport with your reserves intact.
Wow.
The PSR is beyond the isolated island. In reality, you'd never fly past your destination. But mathematically, that calculation shows you how massive your fuel buffer is thanks to that outbound tailwind.
That is a brilliant way to visualize the fuel buffer. It really drives home the relationship between wind and endurance. But the sources don't stop at these simple time-based calculations.
No, they don't.
They introduce a layer of complexity that mirrors real-world heavy jet airline operations. Variable fuel flow.
Because a 300-ton Boeing 777 rarely burns fuel at the exact same rate on the way out as it does on the way back.
Why is that? What causes the fuel flow to change so drastically on a return trip?
There are two main factors here. The first is regulatory semicircular cruising rules. To maintain vertical separation between aircraft, air traffic control requires you to fly at different altitudes depending on your magnetic track. Eastbound flights generally fly at odd altitudes, like flight level 350. Westbound flights fly at even altitudes, like flight level 340 or 360.
Okay, so you're forced to change your altitude if you turn around.
Exactly, and different altitudes mean different air temperatures, different air densities, and therefore different aerodynamic drag profiles. Your engines will burn fuel at a completely different rate at FL 340 than they do at FL 350.
What's the second factor?
The second factor is weight. When you take off, you are full of fuel and extremely heavy. If you have to turn around 5 hours later at the PSR, you have burned off tens of thousands of kilograms of fuel. The aircraft is much lighter.
And a lighter aircraft generates less lift-induced drag, which means it requires less thrust to maintain speed, which drastically changes the fuel flow.
Precisely. So if the fuel flow is constantly changing based on altitude and weight, the simple time-based formula we just used gets incredibly messy.
Which is why the sources provide a specific formula for variable fuel flow that solves for distance directly, entirely bypassing the time calculation.
Right. It skips the time variable altogether.
The formula is distance to PSR equals total usable fuel, F, divided by the sum of your specific fuel burns. Specifically, the fuel burn out per nautical mile. We'll call it KO plus the fuel burn home per nautical mile, CH.
So distance equals F over CO plus CH.
Let's walk through the complex heavy jet scenario provided in the sources to ground this in reality. You are flying a large commercial jet. Your total fuel available, minus all your required final reserves, is 39,500 kilograms. That 39,500 is our F, our usable fuel.
Okay, a lot of fuel.
Your ground speed out is 340 knots, and your flight management computer says your fuel flow out is 6,250 kilograms per hour. If you turn around, you change altitudes due to the semicircular rules. Your ground speed home is 280 knots, and your lighter weight gives you a fuel flow home of 5,300 kilograms per hour.
Now, here's a crucial make-or-break step for the listener preparing for exams. The variable formula requires fuel burn per nautical mile. It does not use fuel flow per hour.
That's a huge distinction.
If you just plug those per-hour numbers into the equation, your calculation will be completely catastrophically wrong.
Right. You must convert the fuel flow per hour into a specific fuel burn per nautical mile. How do you do that? You take the fuel flow per hour and divide it by your ground speed in knots, because knots are simply nautical miles per hour.
Exactly. Let's do the math.
For the outbound leg, CO 6,250 kilograms divided by our outbound speed of 340 knots equals 18.38 kilograms per nautical mile. That means for every single mile you fly forward, the engines consume 18.38 kilos of fuel.
Now for the homeward leg, CH, 5,300 kilograms R, divided by our homeward speed of 280 knots equals 18.93 kilograms per nautical mile.
Now we have all the correct converted pieces for the variable formula. Distance to PSR equals our total usable fuel, 39,500, divided by the sum of our per mile burn rates, 18.38, plus 18.93, which equals 37.31.
So 39,500 divided by 37.31.
The distance to the PSR is precisely 1,059 nautical miles.
It is genuinely brilliant how that formula distills all those massive chaotic variables, shifting winds, changing altitudes, thousands of kilos of weight reduction, variable fuel flows into a single precise distance.
1,059 miles. That is the exact edge of your leash.
It is elegant math. But as we know, calculating a coordinate on the ground in a sterile dispatch office is only half the battle. A flight plan is really just a theory.
Right, because the moment you push the thrust levers forward and take off, reality starts pulling at the edges of your math.
Because the atmosphere rarely perfectly matches a computer model. The air temperature at altitude might be 2 degrees warmer than forecast, which degrades engine performance slightly, causing them to work a tiny bit harder. The headwind might be 5 knots stronger than the weather balloon predicted.
And aviation regulations do not allow you to just put the airplane on autopilot and hope your ground calculations hold up. The sources, specifically the Part Seat operational regulations, mandate strict, continuous in-flight monitoring.
You must perform regular fuel checks to verify the math in real time. For long-range flights, this check must be performed and recorded at least once every 60 minutes. For short-range flights, many operator manuals require a check every 30 minutes.
And it's important to stress that an in-flight fuel check is not just the pilot glancing at the fuel gauge and saying, yep, we still have fuel.
No, the regulations dictate a formal process. It must be recorded in the physical or electronic flight log and evaluated. You are constantly comparing your actual consumption against your planned consumption.
The sources provide a detailed example of a flight log, often called a how goes it chart in older aviation circles, designed for exactly this purpose. The log tracks the flight across waypoints. Let's look at the data provided for waypoints Whiskey, X-Ray, and Zulu.
Okay, let's look at it. At Waypoint Whiskey, the pilot checks the plan. The planned remaining fuel at this exact coordinate was supposed to be 4,300 kilograms. They checked the gauges. The actual remaining fuel is 4,250 kilograms.
So they are 50 kilograms below the plan. Over a long flight, 50 kilograms is negligible, not a big deal.
But the flight continues to the next waypoint. By waypoint XRAY, the planned remaining fuel was calculated to be 300 and 750 kilograms. But the pilot checks the gauges, and the actual remaining fuel is 300 and 660 kilograms.
The gap is widening. They are now 90 kilograms behind the plan. The aircraft is burning fuel faster than the dispatcher's computer predicted.
And here is where the evaluation part of the regulation kicks in. The pilot doesn't just write down 3660 and go back to drinking coffee. They are required to take that actual real-world burn rate and project it forward all the way to the destination.
They have to ask, if this negative trend continues, what will our actual fuel state be when the wheels touch the runway?
And the regulatory red line here is unambiguous. If your trend analysis shows that your expected arrival fuel at your destination will drop below your required alternate fuel plus your final reserve fuel, you have a developing problem that requires action.
More critically, if you are flying to an isolated aerodrome with no alternate and your expected arrival fuel drops below your final reserve fuel, the pilot is legally required to intervene.
You cannot legally or safely continue to a destination knowing that you will land with less than your untouchable 30-minute final reserve. You must divert to a suitable en route alternate where you can land with your reserves intact.
But what if you are already past the point of safe return? What if you are caught in widespread, unforecasted bad weather, or you've experienced a mechanical issue and it becomes mathematically unavoidable that you will land with less than the final reserve fuel?
The sources are explicit about this scenario. If it is certain that you will land with less than your final reserve, you must declare a formal fuel emergency to air traffic control.
The internationally recognized call is Mayday, Mayday, Mayday fuel.
Yes. This immediately alerts ATC that you are in a critical state and gives you absolute priority handling for the nearest runway. No holding, no vectors, just get on the ground.
So, to synthesize all of this material, PEAT and PSR aren't just dry academic exam questions that you memorize to pass your ATPLs and then forget.
Not at all.
They are living, breathing coordinates that you carry with you into the sky. They shift with the wind, they stretch and compress with your fuel flow, they react to the changing realities of the atmosphere around you. They represent the exact, mathematically defined boundaries of your safety margins.
They are the specific tools that allow a commander to make rational, calculated decisions when the environment is chaotic and everything else is going wrong.
Which brings us to our final thought for this deep dive. We've spent the last hour talking extensively about the technical, mechanical side of these concepts. We've talked about calculating these points using distance ratios, wind vectors, and variable fuel flows.
We've treated the pilot like a perfectly rational, unemotional calculator.
Exactly. But the reality of the cockpit is that the calculator is operated by a human being. And as we wrap up, I'd like the listener to consider the profound psychological weight of the point of no return.
Oh, this is such a critical aspect. When you are flying a heavy jet toward Yushu Batang or St. Helena and you physically cross that invisible line in the sky, you are entirely, irrevocably committed to a single tiny patch of concrete in a vast ocean or a high mountain range.
The math we learned today can tell you exactly where that line is.
But as a future captain, you have to ask yourself, how will you handle the human factors? How will you handle the psychological pressure of confirmation bias?
It's the concept of get there itis.
Precisely. Imagine the scenario. You are 10 miles from the point of safe return. You have exactly 2 minutes to decide whether to continue or turn back. You pulled on the weather for the isolated island, and it is starting to look marginal.
It's not terrible, but it's right on the edge of your legal minimums.
You've been flying for 6 hours. You are fatigued. The passengers behind you are eager to arrive. If you turn back now, it means a massive logistical nightmare. It means diverting to a different country, dealing with furious passengers, missing connections, and incurring huge financial costs for the airline.
In that moment, there is an overwhelming, almost gravitational psychological pressure to look at that marginal weather report and say, it'll probably clear up by the time we get there. The forecast usually improves. Let's keep going.
That is the insidious danger of confirmation bias. You start seeing the data you want to see, you start minimizing the risks, simply because the alternative turning back is so operationally unpleasant and exhausting.
The math of the PSR is flawless. It never lies. But the math cannot force your hand. It cannot force you to make the hard, conservative choice. It only provides the boundary.
When the pressure is on, when the weather radar is murky, and when the financial and social pressures of the airline are weighing on you, will you have the discipline to trust the math and turn back? Or will you let human nature push you past the point of safe return, hoping for the best?
That is the real ultimate test of a pilot in command.
It absolutely is.
A sobering, vital thought to leave on. Thank you for joining us on this deep dive into the sources today. Remember, true aviation knowledge isn't just about passing written tests or memorizing ratios. It's about understanding the deep why behind the math, so that when the standard assumptions of flight planning break down, you know exactly how to navigate the variables, manage the risks, and ultimately how to keep your aircraft and your passengers safe.